I'm Nathan Oliva, mechanical engineer. I'm Lucas Bover, mechanical engineer.
I'm Connor Day, mechanical engineer.
And I'm Justin Morrison, mechanical engineer.
So our goal was to make a assisted sun visor for those who are less able, so they can keep their hands on the steering wheel the entire time and have like buttons to press so that when the sun visor goes up, down, or left and right. So like I said, our requirements were to make sure that it's remote controlled, so that way the user can just prompt it with a button. We wanted to make it simple and intuitive to use. We wanted to keep it from obstructing the main windshield, because that is a problem that we get run into, but we're working on it. And we wanted to make it stable and operate consistently. We put magnets in the case, and we think the magnets might have messed up the rear window, so we do have to play with that. But it ran consistently before the climate test.
So for our first prototype, we used the design we left off this last semester. We did the baseline for all our other prototypes, and this include a pod each time. Though in this Mars included said there's no motor, this will be right here, one servo here, one DC right here. When we did we printed out though, we realized that was too large and too obstructive. So, and also the DC motor we were going to put inside of it was not good for position control. So for our second prototype, we replaced the DC motor here with a servo motor and mounted a clamp on it to attach to the sun visor itself. This also allows for the horizontal move once we focus on before too. And also we made it a much thinner design, as you can see here, than the previous one. When we did test it, however, the clip was not attaching well to the sun visor itself. And also we know that the arm length, this arm length right here was, we needed to be sometimes shorter and then sometimes longer, so we had to change that part. So for design 3, we made it into a slide arm instead, which had variable length, which we needed different length for that. The clamp also was much longer here, and we had to screw on to it to secure it better on the sun visor itself. However, when we tested it, the ball joint here was sometimes disconnect from itself when we press the button to pull in the sun visor. And also, we did the servo was way too weak. It was 0.2 millimeters, and it could not pull or push the sun visor. So for our final design, we did a hinge joints instead, which are much stronger. We also replaced the servo motors with servos that are 2 millimeters of torque, and we also made a servo clip over here. It's very lightweight, only coming out 0.36 pounds. The majority of that weight is from the one servo right here. We did have to sacrifice the horizontal one, however, just wanted to focus more on the vertical one to make sure it's going to work well. And also, though, when we were testing, while it could pull the sun visor well, it had issues pushing it back to its own position.
So, as our project is not very numbers and data heavy, we figured we would add just some finite element analysis to show something. So here you can see is a simulation of the clamp. What we did is we anchored the 3 inner walls here as to simulate grabbing on the sun visor, and then we anchored this block down here as that sits in the clamp housing. And then all we did was apply a force on this inner wall here to simulate that pull motion that pulls the sun visor out. And as you can see in that red area, that's where the most stress occurred. In our prototype 3, we actually did have this part fail in this exact location. So what we did is we added fillets in this corner to add material. About the axis of the motor here in the center, it's kind of hard to see everything in dark blue. But if you can tell in these little light blue areas, this is where the most strain occurred. This is because these parts are only around a 1/4 inch thick. And actually, we did, when we were assembling, we had this area here fail on us, so we did have to repeat that part once. And this area, it did deform a little bit, but not enough to break. In actuality, when we're testing, this motor in the middle can only exert 2 Newton meters of torque, so we're well below the threshold of what we would actually experience. And when we tested this design in actuality, we didn't see any signs of breakage or fatigue
And then look at the bit inside of the car actually, as you can see, it does pivot quite well, but it comes into some problems. We're gonna have to push it back, as you can see, it's right there. It struggled to push it back. Probably due to the fine arm design we have here.
So here is our full assembly drawing of the device. It was printed in PLA. Here is the window hinge piece. So to make it easier to print and easy to assemble, we put some T slots kind of right here, so that when we stuck the pin in, we wouldn't have to worry about the pin rotating at all, and it made it tight and good fit. Then here is the X slotted arm, where the servo would go right here. The servo attachment we decided to use was the X piece, as it provided the most surface area for movement. And to fully attach the servo motor to the arm, we used screws that came with the servo set. This is the sliding arm design. It was designed to solve our variable length problem. However, one of the downsides of it is it doesn't have enough friction to hold itself in place while trying to push the sun visor back, which is one thing we will be looking into in the future to fix. This is the compartment that holds the servo. The servo is slotted in here and tolerates well enough that it is a tight friction fit. Then these slots here are where the sliding arm goes, and it is a pretty loose fit. Here is the clamp hinge. This is very similar to the window hinge, with the addition of this spot here, where giving it some good structure and rigidity. The reason we made the clamp a separate part is because it was the part that was most likely to fail, as it was under the most loading and it was holding on the most. So in order to increase our prototyping speed and decrease print time, we decided to make the clamp a separate piece that could be easily slotted out and slotted in. We did experiment with different sizes of clamps. That one was wider. The only downside is that the sun visor had a rounded off bottom, so the height of the clamp is very important in order to get to an area where it's more rectangular. This is our remote. Here, the button on the left we designate as the push button. This button resets the servo to the home position, which being 0 and under roof. And holding the button will move it in small increments towards the driver and closer to that home position. Then the right button, which we designated the pull button, this sets the servo to the next position, either being 90, 135, or 0 degrees in that order. If you hold this button, it'll move it slowly towards the windshield.
So our initial idea when making the remote control was we were just thinking about buying something off Amazon, making it simple for ourselves, and having it be able to hook up from the remote to something to plug into the Arduino into the actual visor arm. However, we actually went with this setup with the help of Dr. Zhu. He provided us with this transceiver module, the NRF24L1. So what essentially we're doing here is we have two Arduinos and they communicate with two of these transceiver modules. So we sat down, we got help from Dr. Zhu, we sat down with ourselves, and we figured out how to wire these and set these up so that they can communicate. Basically, the Arduino is powered by a 9-volt battery, and you simply plug in the push and pull switches into the Arduino, and based off our code, the two switches do as it would like. And then here's just the receiver module. This is the part that's attached to the arm. Again, Arduino is powered by a 9-volt battery. The transceiver module, simply enough, they were about wired the same exact way. The only difference is here, since we had the motor, we had to power it with a separate 6-volt battery pack. This is also partially because towards the end of testing, we were coming into some issues with drawing current. So we couldn't simply have the motor and the Arduino powered by 9-volt. We had to give it its own separate supply. And
so here is our code diagram. It begins once the AbleShade device is turned on, and once it's on, the remote waits for a signal from either the pull or the push buttons. The pull button is not held down for 2 seconds. it would set it to the next angle, either being 0, 90, or 135, and then reset the angle for a signal. If you decide to hold the button, it would add 15 degrees to the angle, and if you're still holding the button and the angle is not at its maximum, it would continue to add those 15 degrees until it either reaches the maximum, in which case it resets it to 0, or the button is released, sending the remote back into a created signal. The other button, the push button, has a very similar code setup, where on press, it'll just reset the servo to 0 degrees and send it back to your group. If you do hold it, it'll subtract 15 degrees from the angle, and it'll continue to do this until the angle is 0. The reason we have it set to 0 when it's 0, which seems pretty counterintuitive, is because the way the code works is the angle is just the value stored in the code, and if we kept subtracting 15 from it, it would become negative angle, and that doesn't do anything for the servo, and it would just be a headache.
Okay, just a little bit of ethics. We don't want to really get into the nitty-gritty, but the basic thing is that ethics is a very important part of our project, simply because driving can be very dangerous. And all we want to do is try and make driving a little more safe for the people who might have a hard time keeping control of their vehicles. So under the code of ethics, we are to uphold the safety, health, and welfare of the public. And we found that when we installed the AbleShade in our car, it was a lot more bulky than we had initially imagined. However, it does stay out of the legal obstruction zone of the windshield. So in the upper sweeping edge of your windshield wiper, you have about a 7-inch clearance, and at the bottom sweeping edge, you have about a 7.5, 8-inch clearance. So we were in the middle, so we were good with that. But for these reasons, we deemed our project more of a proof of concept rather than a marketable device.
Here's our budget. Most of this came out of pocket because we might pursue a patent in the future. And the total balance was about $153. Some of our parts we got from like various labs that we had previously on campus, like robotics, 3D Arduinos. And in summary, we were able to get the code to do pretty much what we wanted it to do for the up-down motion. We couldn't figure out safely how to turn it without like it slapping into the driver's face on button press. We proved that the idea itself is functional, but we will need maybe a little bit more time to smooth out the edges. And we've experienced all the wonderful stages of manufacturing and research and development, even though for most of it was stressful, but a fun learning experience. And our future goals for whenever we meet up again, we want to reintroduce that rotational motion. We want to maybe make it a little bit more of a smaller profile. We might look into better manufacturing methods instead of 3D printing for like stronger plastic or maybe better adhesives, better stabilization, and our receiver module is kind of just crammed into a box right now on the table. We want to maybe make that more aesthetically pleasing. Thank you to everyone on this list. Dr. Anaya for being a wonderful advisor, Dr. Z for all of his wonderful electrical knowledge, Mitch Adams for everything he's done for us, especially with our sheet plexiglass that we had to make safe for us to test on. Ms. Cherry Chase for everything she's done and maybe even some future patent work. Dr. Gamari, who isn't here right now, but he helped us try to figure out our old idea of using a solar module. And Dr. Bednarz for everything he has done, all the help and assistance he's provided, and just being a really cool professor here on campus. Our resources. Do we have any questions?
Thank you. Now you're going to make me feel bad. I'm going to put you on the spot a little bit. It's part of the process. Okay, so can you go back to slide 8, please, where you had your FEA? It's a good thing that you did an FEA and that you wanted to pick one of the components that possibly could fail. And just caution when you present the data, you're talking in terms of stress, but then you're presenting in strain. You just want to have that match. So, it would have been better if you could put that in von Mises stress, and then you could compare more directly. Okay, here's our yield strength, and and here's what the stress level we're seeing, then it translates more directly to a safety factor. Okay, yeah, we're nowhere near breaking that tab off or whatnot. So just kind of have to comment on that. But then I guess a question then, what other materials would you be looking into? You said that you may investigate stronger plastics or possibly metal. Which one, if you had to do the 2.0 version, which one would you go to next?
More likely it wouldn't be made out of metal just because in the case of an accident, that to come flying, a metal chunk like that come flying at your head, that would be very dangerous. So probably just a more strong plastic, what is the other one? ABS, yeah, sorry. Instead of PLA, so that would be our probably next step.
Yeah, good answer, yeah. It's thinking about the safety concern about having metal as well. Okay, more questions?
I know you said something about it. Go to your flow chart, please. Right there. Okay, so on the top part of the loop, you're incrementing up. On the bottom loop, you're decrementing down. But at the right-hand side where your question is, angle is not 135 degrees, and then the bottom one, the angle is not 0 degrees. So you keep looping back around and decrementing or incrementing as so. But then you come down into this nose step, and on the top thing, you're trying to drive to 135 degrees, yet you set the angle as 0. So all of a sudden, you know, you're trying to drive it to the 135 degree point, and then you set the angle to 0. So what happens? Does the thing all of a sudden go move the visor or back to the 0 point?
So what happens is the visor will reach that 135, and then in the code it's an if statement where if it's 135 it sets to 0, so it's not trying to do both at the same time.
So why are you setting the angle to 0 if you're trying to drive to 135? That's what I don't understand.
That is mainly just like if you just kept holding the button, it would kind of just send it back, because originally our design we only had one button working, where now that it would just kind of keep going back. I do see your point though.
I'd be curious to see what the physical reaction is going to be, because when you set that angle internally into the device to 0, all of a sudden this thing's you're going to 135, and then when you hit that 135, it's gonna back up. You know, that's what I see in the flow chart. So I would think that logic through.
Okay.
More questions?
Thank you guys. So, like when you were demonstrating in the car, if you kind of didn't come back, like that failure, was it mainly mechanical or communication issue?
I'd say it was mainly mechanical, because it's an issue on our sliding arm, where that the friction on the sliding arm is less than the friction that it would take to move the sun visor. So since it was the weaker point, it just went and pushed it back.
So I kind of appreciate, you guys did like 4 or 5 different iterations of model, like the prototype, right? So I'm wondering, like after 4 or 5 iterations, why that problem was not resolved? If it's just a mechanical, you guys are 4 mechanical engineers, I would expect that mechanical system to work a little bit better, a little bit more reliably. I mean, if you tell me if it's because we lost communication and the communication was not reliable, I kind of understand that, but again, we have 4 mechanical engineers here. We have a relatively straightforward mechanism here, and why we couldn't function in a more reliable way? That's my question. Why do you think? Is it just out of time, or you see what I mean? Like, is it possible, like, give you 1 more iteration, you can actually make it function in a more reliable sensor? Is that possible?
Yeah, definitely. One of our concerns was that we would do that. We were thinking about adding some sort of like stopping mechanism on it, because we definitely don't think it needs that whole arm.
Or is it because, like, when you were testing the vehicle, it kind of came as a surprise? Because like, most of the time you didn't test in the vehicle, then you only tested in the vehicle like almost 1 week before the deadline, and it just ran out of time before you can actually do another iterations and try to fix the problems. So was it, looking back, do you wish you would have started testing the actual vehicle 3 weeks earlier so you can do 1 one more iteration to resolve that issue. That's
Yeah,
it.
most definitely. One of our actual main problems we ran into is at a certain point, we kept trying to bring the remote into our car. So we do a test and start. We bring the remote into our car, and then the remote would not communicate with the two Arduinos, which is very strange. We could not figure it out. So if we were able to figure that out, we definitely would have done more mechanical testing.
Okay, but still, I still appreciate, like, I understand, because I spent 2-3 hours to help work on that, and I understand the frustration and how much work you actually put into that. Even it didn't work out like in a perfect sense, but still, that effort and experience was still very, very valuable. Okay, so just when you were doing the stress analysis, right? What material were you using for your model?
The model was actually out of ABS because SolidWorks doesn't have PLA, or at least I.
Well, then that's going to be very, you see, like the 3D printing material that, PLA is very different. I mean, even from density, from you see, I mean, like 3D printed parts are definitely not homogeneous or even like solid. So your material is very, so that's, I mean, again, anytime we do a final element, we want to make sure it actually adds to the value of your presentation, not just do it for the sake of doing it. That's just my comments. Okay, thank you.
Okay, more questions?
Is this something that you have to like recalibrate every time the window pitch is different, or is it universal for all different window angles, like on a car versus on an SUV?
Well, we actually modeled it originally for Luke's car. And then the one picture, I don't know if anybody saw, but in the very beginning, we had installed it in my car just to get like a better view. And we noticed when we were installing it, it actually didn't fit quite well. So this is something that we did essentially for just Luke's car. But if we were going to make it modular for many cars, that's something we obviously have to work on.
Would it be just adjusting the final angle, really? The angle of the windshield change? Or would there be other calibration?
That possibly increasing the length of that slider arm, because we found that after prototype 2, we needed to have variable length, and we didn't know how much it needed to change, so we just had that slider arm go a good distance so we could cover any variable length changes.
So I guess the placement of the visor could vary too, based on vehicles. The length of it, how far from the windshield, so yeah, it might be almost custom made for a particular model. Okay. Any other questions? Okay, thank you, Tim.